Hello, everyone.
Hi, Paul. Yep, can hear you. Sorry for any of those technical difficulties getting you on. Glad to have you here.
Very worrying, but I'm now available and correct.
Brilliant. All right, I'll hand over to you to kick things off then, Paul. Thank you.
So welcome everyone to this next roundtable on emerging technologies with a second session that we're running now on space-enabled net zero by 2050, looking at some new opportunities. We have a very esteemed panel today and some wide-ranging topics to cover that are focused on net zero. And if you haven't seen the agenda, I'm going to just quickly outline it for you. We're going to have an introduction by Amanda Campbell, who's our head of net zero at Satellite Applications Catapult, and she will really provide some of the context for the need to address this net zero challenge and what the space sector might need to do to actually respond to the opportunities. And we have one main session today with 4 talks covering some aspects, the technical aspects, looking ahead at future technologies. We've got David Humphrey, who's going to describe some of the work that we're doing on space-based solar power and how that might contribute to a future net zero carbon economy. We have Dr. Anur Salik from University of Glasgow, considering an alternative approach to exploit the solar energy by using orbital solar reflectors and some of the opportunities and challenges that they will bring. We have a third talk from Dr. Andrew Wilson, who looks at the actual space sector itself, the emissions and how to minimize them and to improve the life cycle to make space itself sustainable so that it can continue to contribute to the global economy. And then we also are going to look at how do we measure these things and make sure that we're doing all of the right things, looking at UK Earth observation capabilities and bring that into effect to help on the challenge with regard to space supporting the climate agenda. We'll then have a panel session where all the panelists will come together, and I'll be looking forward to receiving questions from everyone in the audience. I'll be avidly watching the chat and the questions. Please use the questions session, the active session, to actually pose your questions, and I will try and orchestrate them and put them to the panel towards the end of the day or end of the morning. So without further ado, I'd like to introduce Amanda, who is going to really set the context for the challenge ahead with regard to net zero. So Amanda, would you like to take the floor?
Thank you. I'm sharing my screen. So good morning, everyone. Fantastic. Checking. Fantastic. Just checking everyone can see my screen before I jump in. Fantastic. So good morning, everyone. So I'm Amanda Campbell, head of Net Zero. I'm going to be talking to you today about emerging technology and really setting the scene of why net zero, why it's important, and how we need technology to accelerate us there. First of all, setting the context, there's been a correlation for hundreds of thousands of years between CO2 and temperature. Never before in human history have we gone above 400 parts per million. The last time was in the Pliocene, which started 3.4 million years ago, and the world was not in a habitable place back then. Carbon is accumulative, so every year, the more we release into the atmosphere, the more it builds up. In order to stop warming, we need to stop CO2, and that is essentially the basis of net zero. We need to have a balance, essentially a accounting perspective, where we need to have a balance of greenhouse gas emissions into the atmosphere that we're taking away. There are different pathways to net zero. 1.5 is very critical, and it's about halving emissions by 2030 and achieving a net zero by 2050. And to achieve net zero, we'll have to reduce as much as possible and rely on carbon offset technology for the residual amount. It's critical to drive it down as much as possible because we can't offset the sheer amount coming from giving off by human activities. Previously, so this blue line, the very low emissions down here is the 1.5 target. One above the green is the 2 degrees target, and research shows that essentially it's not fast enough, it's not good enough, and which is why we've driven it down. This mid-level emissions is essentially the outcomes of COP. So even if we were to achieve the policy commitments from COP, we're still very far from the 1.5 target. And in fact, we're actually on a higher trajectory, which is going to result in significant warming. And the IPCC's most latest report is showing that the consequences of warming is far more significant than we previously expected. Today, 3.3 to 3.6 billion people live in contexts that are highly vulnerable to climate change. Today, we're at 1.1 degrees. And as you can see from the table here, even a slight 0.5 degrees has significant cost on the planet, on people, on economies, caused by extreme heat, droughts, flooding, etc. If we continue on the trajectory that we're going to miss 1.5 to maybe even 3 degrees. And by 2100, 50 to 75% of the global population are going to be living in life-threatening climate conditions. So essentially 50 to 75% of the population are at risk of dying from the severe heat. So this is literally life and death. And this is really the decade of delivery of driving down reductions and driving solutions. One massive positive outcome of COP was the private sector's commitments aligned with net zero, from the financial sector to private companies setting science-based targets. Science-based targets are really critical to our transition to net zero. It's very clear that we can't essentially stop emissions straight away, can't stop them tomorrow. And even from COVID, when the whole world was stopping and pausing, we were still having significant emissions. Following science-based targets is essentially a trajectory so that we can align with 1.5. And it's critical to set a near-term reduction and to reduce emissions as much as possible within the next decade. And by 2050 at the latest, reduce emissions to almost about 90%, and offsetting with certified greenhouse gas removals, which is the purple line here. It's very important also to encourage technologies and invest in technologies which can support this transition to net zero. And even if they don't account to your overall global commitment, this abatement and investment is very, very critical. And this is going to be a lot of what we're going to be talking about today, potential technologies. What is the cash pot doing for net zero, and what can you do as a company, as an individual, or maybe in your future careers in different companies? Well, first of all, we joined the Race to Zero campaign, and I encourage every organisation to look at this as well. Under the Race to Zero campaign, there's different bodies. We're part of the SME Climate Hub, which gives guidance for companies just like ourselves, but there's also guidance for academia, large organisations, and specific bodies. The Race to Zero has 4 pillars and structures and guidance. And pillar 1 and 2, it's about reducing your company's emissions. Pillar 3, it's about integrating climate into your business strategy. And lots of companies can be doing that today as well. So identifying where are their capabilities and opportunities aligned with their USPs and how they can really accelerate to net zero. And then finally, how can we influence climate action in society? So how can you be supporting other sectors, being advocacy, and making change in your workplace, in your society, etc. For smaller companies, I recommend looking at the 1.5 business playbook, which has more details on the guidance here, covering not only just reporting of your emissions, but really about implementing it and driving the change. So let's set a bit of a scene for the context of satellites and their role in net zero. So satellites have played a critical role in driving the policy now it's really, we need to drive action. Over half of the essential climate variables are measured exclusively from space. And this has been used to inform the policy, the IPCC, and the bodies to really drive the policy coming out. The capabilities and the applications are constantly evolving. We're getting new data sets and new metrics from more precision in methane monitoring and CO2. We're getting more evidence and verification, and we're increasing the processing capabilities. So essentially we're getting more data, more accuracy, more precision, more points of data, which is giving us a better understanding of the Earth and the actions that we need to take to tackle climate change. So linking back to the point earlier on strategy and opportunities, looking at broadly about the satellites strategy in 3 core areas: geospatial intelligence, access to space, and ubiquitous connectivity. The focus of this course is predominantly around access to space ubiquitous connectivity, whereas the last one was very much on geospatial intelligence. And Krupa's going to come in at the end from Space for Climate to give another overlook at geospatial intelligence to tie this together. There are opportunities in every single sector for satellite technologies to transition to net zero. And it's really critical to identify where their key gaps are and the barriers, to identify the solutions and drive the innovation. I'll speak very briefly about this, geospatial intelligence, because it's covered more in the last talk, but predominantly it's about, there's a lot of opportunities from measuring, reporting and verification, starting from natural capital, so identifying hotspots such as peatland areas, which need to be preserved and how to restore them, nature-based solutions, carbon offsetting projects, and how we can verify them and identify them. Supply chains, identifying with geospatial locations and verifying sustainability claims from different corporate sectors. Green finance, identifying risks and vulnerable sites to climate change, supporting the financial sector and companies on their ESG metrics, supported by the satellite data. And again, with the risk in the infrastructure, assessing sites which are vulnerable and how they need to adapt and build resilience. And then finally about energy exploration, so identifying hotspots for solar panels on roofs, etc., hotspots for geothermal, minerals, which we all need to, for instance, like the shortage of EV batteries, and critically the stresses on productivity and how we can support the supply chains with them. Now jumping into ubiquitous connectivity. So it's all about connection and efficiency. In line with net zero, a lot of this aspect is about if you envisage what you want the world to look like in 2050 or in 2030, how is technology going to be supporting that and how can it be used to accelerate? So for instance, Internet of Things and networks, how you can drive efficiencies to turn on and off systems and how we can all connect to the grid and be more resourceful. Autonomous EVs, how you again support them with the power and the EVs and the efficiencies, and with internet access to all, what solutions can be driven, what efficiencies can be made, and access to technology. An area of precision farming with efficiencies, reducing waste, smart grids, and then supply chain transparency, particularly on scope 3 reporting, utilizing technology like AI, blockchain, and then exciting business models like non-fungible tokens and carbon credits, and how we can use these support systems to support offsetting and also reporting. Now, this is going to be the primary focus for the talk, which is about really exciting technologies coming more broadly from the space sector. David Humphrey is going to be talking about space-based solar power. There's other areas as well, such as mining of minerals from space to support battery and EV and the transition in order to get there. Areas of nuclear reactors, which are exploited for space and how we can use them at local grids and smaller units here on Earth. Dr. Andrew Wilson is later on going to be talking about the environmental impact of the sector. There's areas such as launch, fuel, understanding where the fuel emissions are at different points in the stratosphere, understanding the impact of manufacturing and the impact on supply chains, and particularly on a lot of the largest part of the sector is predominantly around downstream, so the impact from data processing and how we can drive efficiencies of that. And then I also want to open up the question of cross-application of technologies. This isn't really an area we've spoken about or explored much. What technologies are being developed for exploration in space, which in their kind of closed system can be applied here on Earth and drive innovation for net zero. So overall, I want this talk to inspire you to think of actually, there are these really exciting technologies. We're going to go through examples today. Really open up and think, what is the potential of what you're working on at the moment and what can be applied here, and what, as I said earlier, it affects, there are opportunities in every single sector. So there might be broader and more immediate solutions down here on Earth you can try. So I'm going to pass it over now, and I hope this talk can inspire you to think of lots of ideas, and we'd love to work with you or hear from you if you've got any. Cool, passing it over. Is it to David Humphreys next?
No, I'll take it. Thanks, Amanda. So
Cheers.
That's great context. One of the things that I think that came to mind as you were talking is one of the things we need to look at is how do we create this new economy, the new zero carbon economy? How do we create the demand for services that are going to motivate industry to invest, to actually provide capability? What is the role of the international regulatory communities? What's the role of regional government, local government? And how do we stimulate the demand? So maybe this is something we can come back to on panel. But right now I'm going to hand on to Gilles, who's going to introduce the remainder of the panelists and also the talks that are going to be presented. But thank you so much, Amanda, for setting that context.
Good morning, everyone. Thank you, Paul, for the introduction, and thank you, Amanda, for the great introduction talk. So now we have a lineup of 4 talks, and then we're going to have a panel discussion. So we encourage the audience to ask questions, but please put that into the question and response box and not in the chat. That will really help us to track the questions and to make sure you get an answer. So to start, please join me in welcoming David Humphrey from Satellite Applications Catapults. David, if you want to share the slide.
So just sharing now, screen 2. Can you see that? That looking good?
Yes, that's really good on my side, yes.
Well, thank you, Gilles, for the introduction. My name is David Humphrey. I'm the space energy lead for the Satellite Applications Catapult, and I'm also the technical lead for the Space Energy Initiative, a UK membership of different organisations in academia promoting the UK attempt to build a programme to develop space-based solar power. Let's try. So to reiterate what Amanda said, and she gave a really good background there of what the issues are with net zero and the many challenges. What I would like to kind of pick up on what Amanda said was the race aspect and the speed aspect. And that's where I believe the main fundamental challenge of net zero is. Yes, we have to do a number of things. Yes, we need to make societal change. Yes, we need governmental change, but it's the rate that we need to change that concerns me the most. So by 2050, we need to have replaced around 40 billion megawatt hours. And with around 10,000 days, that goes to about 4 megawatt hours per day. When you look at the various power generation methods, you can start to see that a single energy technology will not be able to provide you everything. If you looked at, for instance, a nuclear new build, you would start to need to make one of those per week in order to meet this challenge. So what I'd like to leave you with is that idea that there is no silver bullet. We need to accelerate low carbon technologies that are already developed, and we need to do it now. We need to increase the build of renewables, solar, wind. We need to incentivize energy efficiency, but also we definitely need these new build nuclear. But also behind that, we must be developing new low carbon technologies. From the current technology cluster, all we really have is fission. So we need to get a more broad portfolio. So if we could take one of our renewables, such as solar, and make that base load, that would be an amazing new technology to use. If we could collect solar in space, we'd have about 13 times more solar available to us than if you take a normal UK average. If we could collect it in space, we would have no day-night. We would have no problems with the atmosphere. And within a small strip within geo, you have about 100 times more energy and than you would need by forecast. Now, by no means we're saying that it just needs just space-based solar power, but this is another technology that could become part of the energy portfolio. So net zero has many challenges, and I'm not going to keep telling you the same thing because I'm sure you all know. But what we know is there are a number of pathways that I've already mentioned. We need to accelerate renewables, we need to accelerate nuclear, and we also need some forms of energy efficiency and some forms of societal change. But also we need our energy to be affordable and reliable. We can't have people in energy poverty. We need to make it scalable. But there's many challenges in doing that because, as I say, there is a real need for a base load. And a lot of the things that we're currently researching has a lot of immaturity. And of course, we need to make it affordable. And we believe that space-based solar power offers some of those options. So just to give you a little bit of background on what we're talking about a really large spacecraft. It is going to be significantly larger than the International Space Station, but it's quite sparse. So actually the kilograms, the tonnage of this is not, so it ends up being around 1 kilowatt per kilogram. So we have some big mirrors, they look like the CDs in this picture, that bounces the light onto photovoltaics. And then we create radio waves around about 2.4 or 5 gigahertz. And in that wavelength range, it makes it quite invisible in the to the atmosphere, so you can pass. And even when there's heavy precipitation, we believe that at least 95% will be able to get to it. You then have a large ground receiver, so it comes out to around about kilometers inside the receiver, but actually it's significantly smaller than when you're looking at, for instance, wind power or the same sort of size for solar. And of course, it's baseload 24/7. So why are we now thinking about it? Well, it's because space launch has significantly reduced. If you look down in the bottom left-hand corner, I have a very love-hate relationship with the space shuttle. It was one of the most fantastic things I'd ever seen as a kid, but also it was really expensive to launch stuff. So around $65,000 for every kilogram. But as you see the commercialization of a launch with people like SpaceX, you've got Blue Origin coming up, and many UK launch providers are also starting to develop rockets. We expect that cost of launch to reduce significantly. And if SpaceX actually develops their Starship, or similar companies develop fully reusable heavy launch vehicles, then we really are talking about being able to lift quite heavy mass. But also space hardware is also reduced significantly as well. We have lots of technologies that were developed from terrestrial that are very useful for space-based solar power. And so all of this combined makes it now start to become viable. So a number of years ago, Fraser Nash and the Satellite Application Catapult launched a thing called the Space Energy Initiative. And now I believe we're about 50 members. This is in industry, both large companies such as Thales, such as Airbus, some SMEs, some academics, and the Catapult Network, all working together in working groups to develop the program which enables the UK to be a leader in this technology. And so it's a really exciting time, and it's not just the UK. The Americans are extremely invested in this. We have work in China, in Japan, Australia is interested in this, Europe as well. And so it's a really exciting time. So we've set ourselves a challenge. The criterion with our challenge is that within 12 years, we want to develop a commercial, equitable, and sustainable baseload electricity products using space-based solar power. We've used these words quite carefully. It has to be a commercial product in order for us to get suitable investment. It needs to be equitable, because if the whole world doesn't meet net zero, none of us meets net zero. And it needs to be sustainable, because we need to be able to put many of these satellites up. And therefore, you will hear from Andrew later on, the requirement to make space sustainable. So this is my last slide. And I want to talk, and I'll talk a little bit about this last slide. So on the left-hand side is, can we afford to develop space-based solar power? And on the right-hand side is, can we afford not to develop space-based solar power? So on the left-hand side, we've created a 12-year program where we are producing demonstrators in the first 6 years of phase 1 and phase 2, where we will, in phase 1, we will deploy a balloon where we'll fire power from the ground to that balloon, a tethered balloon around 2 kilometers in altitude. We will also do some form of robotic assembly. And at the end of phase 1, we want to de-risk space-based solar power, that there are no fundamental technological challenges in our way. We want to learn, we're going to build, we're going to break, and we're going to keep iterating really quickly. We're going to work with industry, and we're going to be as quick as possible. In phase 2, we want to demonstrate all the activities of space-based solar power. So we're going to try and produce around 6 megawatts from space. And then as we move to phase 3 and phase 4, it's about the commercialization. Phase 3 will put around about 180 megawatts spacecraft up there, where now you're really delivering and understanding the commercial side of space-based solar power. And then phase 4 is where it's industrialized. It's all about the gigafactories. It's all about manufacturing and throughput. Space-based solar power should be more thought of as being a mobile phone producer than it is as a large spacecraft. We're going to build lots of modules, and we're going to assemble them in space. We developed this program to be half of the cost of a nuclear new build. Now, by no means are we saying that we should stop nuclear new builds. In fact, we must accelerate, and we must accelerate now. All we're saying is that space-based solar power, the program is affordable. It's comparable to that of a nuclear new build, less than that. But the issue is, can we afford not to do it? We have so little time that we need to be developing and researching any technology that might give us a net zero advantage, anything that helps us to accelerate. We're running out of time. But the beautiful thing, and space-based solar power is a massive challenge. It's going to be similar to an Apollo mission. It's going to be similar to a Manhattan project. And we shouldn't forget that. This is not an easy thing. However, it is so valuable to do these things. If it was to succeed, potentially there's 20% of a $5 trillion a year energy market that we can access. There are so many spin-outs and spillovers, from materials to wireless power beaming to high concentration PV to robotic assembly. We can inspire the next generation to take part in this net zero race. We can create jobs and marketplaces and regional growth, and this is a valuable challenge. And I think I'll stop there, but just to say, this is once in a generation project, and together we have a really good opportunity in actually doing it. Thank you.
Thank you very much, David, for this very exciting presentation and projects. So we are just running slightly behind, so we're going to keep the questions for the panel session. So again, for the attendants, don't hesitate to ask questions, and we're going to go over them in the panel discussion. So now it's my pleasure to introduce Dr. Onur Selik from University of Glasgow. So Onur, if you want to share your slides, please.
Can you see it?
Yeah, perfect.
Okay. Hello, everyone. As David explained, most of space-based solar power is a very exciting project. I'm going to talk about something a bit more authentic, as Paul noted nicely. So I'm part of a project called Solar Space. We are investigating the concept called orbiting solar reflectors. A little bit of a more a more straightforward concept than space-based solar power, and I'll be talking about as the details of it. And when we talk about clean energy and the whole climate change, I think the first thing that comes to mind to use as an energy source is the sun. And according to some research, by this year, the total solar PV capacity is supposed to surpass 1 terawatt level. But this is both small and large scales. What we concentrate here, though, is the large scale solar power farms, which has something more than 500 megawatts or higher, to give an example. And there are some 10 or 12 of those all across the earth, and we can only expect that this will grow both in size and capacity. But as much as we would like to increase this capacity, I think that one of the challenges of terrestrial solar power is really the daylight only limitation. Apparently it's about 25% of the year we can actually use the solar power, and there's nothing we can do about it because Earth is rotating and we have nights. The idea with orbiting solar reflectors is really to address this daylight only limitation and extend the days on solar power farms locally at night hours or more critical hours such as dawn and dusk. In this case, the orbital solar reflectors is really large, thin, kind of flat reflectors that intercept sunlight in space, which is always available, and redirect back to the image of a solar disk onto a solar power farm. It really is to extend the day on a solar power farm. And again, as the earlier presentation rightly put it, the whole falling launch costs and advancements of some of the other space technologies, such as on-orbit manufacturing and assembly, makes an exciting venture for this time, and this is why we think is a good time to focus on this. And if the concept still looks a bit futuristic, I think this example will explain this much better. This is a southern Norwegian town called Rjukan. It's situated between a valley, and it doesn't get sunlight for some parts of the day. And what the residents of this town does is actually putting a solar reflector on top of a hill and reflect the sunlight to the town center. And I think this explains the concept quite well. What I meant by extending the day locally is literally only on the town center, and it's a dispersed light, so it's not exactly a full daylight, but it's enough to I think have a bit of light in that region. And that would kind of allow the city residents to work and do their things during the day as well. But historically speaking, orbiting solar reflectors are not exactly an old technology. The mention of this thin flat reflectors illuminating airports and stuff are already in the book of Hermann Oberth in 1920s. And with the oil crisis, there's a huge increase, and especially in US-based researchers and NASA itself working on this concept in 70s and early 80s. And there's even a tech demo mostly on the solar sailing and reflecting illumination applications by Russians in 90s. And with the whole climate change and the acceleration of this process, actually there's the interest growing again in 2010s. And we started our solar space project in 2020. That was, we are 4 of us now, led by Colin McInnes. We are all working on the orbital attitude control, reflector structure and economics aspects of orbiting solar reflectors at the moment. I think I've already mentioned quite a bit of it, but I think it's worth mentioning and comparing and contrasting a bit with the more current approach of space-based solar power that David mentioned. And I think with the orbiting solar reflectors, we have a bit more straightforward concept by just reflecting incoming sunlight from the sun to the ground. Technology is lightweight and simple, and it's actually available through solar sailing, and we have that's already flown many times in space, and we typically consider a low Earth orbit, and as a result, because our past durations would be lower on a particular solar power farm, then the delivered energy will be much lower than solar power satellites. Although it gives the flexibility of having decoupled from any ground-based system, and just by choosing an appropriate orbit, we can just put our ground trace on any solar power plant. And again, another potential disadvantage is there's a bit of a seasonal variation, because it's affected by the seasonal variations because of the nature of the physical resource that is delivered to the ground. I think one of the questions might be how much energy we can deliver. Just consider a 10-kilometer diameter solar power farm serviced by a 1-kilometer effective diameter structure, which could be just a standalone 1-kilometer structure, or it's just a couple of reflectors coming together in some sort of a constellation. And our calculations show at the maximum it's about 33 megawatt hours energy delivery in about 17 minutes. And this can be done daily with the, again, appropriate choice of orbits. And according to the resources I was able to find, this is equivalent to the yearly mean yearly electricity consumption of an average UK home in 2020, which might be increased by the whole pandemic situation, but there we are. And again, according to some other research, this is about removal of about 30 tons of carbon otherwise to be released to generate the same amount of energy by a conventional coal power plant. As I said, energy delivery can be increased by additional reflectors, but what this technology can do is to provide clean energy to, say, a medium-sized town, just by illuminating the solar power farm about 15 minutes a day. And at the same time, it can remove the carbon to be released to the system by reducing the usage of coal or other fossil fuels. And this webinar is all about new opportunities. So I think it's also important how orbiting solar reflectors can actually influence the terrestrial solar energy expansion as well. Here the figure shows global mean yearly installation. It's a bit of a dated data, but I think the overall features are the same even today. And the white dots show the large solar power farms, and this is the orbit. The black lines show the orbit ground trace, ground track. And we can already see some of the red regions that the orbit passes, where new solar power farms can be built, which would be utilized by both day and night, and therefore can also be serviced by orbiting solar reflectors at night, as well as they can be used during the day. And this is just one orbit that's chosen from a virtually infinite number of possibilities. So the orbits can, again, be set in different ways to service more solar power farms. If we go one step further, because of the nature of the physical resource that we send it to the surface, as in the sense of sunlight, we can actually use enhancing biofuel production by providing additional solar energy to open pond, sort of algal ponds or photobioreactors at night, which would be a resource that orbiting solar reflectors can deliver. There are a bunch of carbon capture technologies that can be enhanced by solar energy, which reflectors can also help here. There are various geoengineering proposals, and on the less of sustainability, but more of a, I guess, a different ways of looking at things is that reflectors can actually provide on-demand illumination in disaster areas as well. And I wanted to discuss this because I think in every step we take in the soul space project, we take the regulatory discussion at heart, and there are both terrestrial sustainability and space sustainability is in our minds when we are designing and assessing the feasibility of the system. And there are different aspects that we are looking into and try to answer the questions regarding those, such as end-of-life disposal of these reflectors, as well as space debris problem, potential stray light and ecological impacts there, and as well as the impact on ground-based astronomy, which seem to be a recent discussion, and with the increase of small constellations in space. And for all of those, we have either different arguments or potential solutions, and we will be working further to make sure that they are all answered, and this technology can be applied effectively when soon enough without any problems. With this, I'd like to thank you, and I'll give the mic to you, Jill.
Okay, thanks a lot, Onur, for this presentation. So we're going to directly move to Dr. Andrew Wilson for the second presentation from the great city of Glasgow here. So Andrew is from University of Strathclyde. If you want to share your slides, please.
Okay, can you see
me?
Yeah,
we can see it perfectly. Thank you.
Okay, great. Thank you very much. So yes, today I'm talking to you about space sector emissions and the sustainability of the space sector itself. So firstly, what actually is the problem here? Well, the space sector has actually been quite slow in addressing its own sustainability, and one of the main reasons for that is because there's a lot of exemptions which have been granted in the space sector. For example, the Montreal Protocol on substances that deplete the ozone layer actually didn't actually address launchers, despite being the only form of anthropogenic emissions to emit ozone-destroying compounds into the atmosphere. And on top of that, European Commission directives such as restriction of hazardous substances also grant exemptions. But we need to actually look at, are our operations themselves actually sustainable? And really, we're at a point where we realise that we no longer can just pollute what we want. But we also need to make sure, that our solutions themselves are also sustainable. So, for example, what we mean here is that if we have, for example, mega constellations and we want to get them out of the way, out of orbit, we maybe want to re-enter them. But does that just add metallic compounds into the atmosphere? Therefore, you're replacing one problem with another. On top of that, another issue is that, of course, we need to be able to actually measure what we want to kind of talk about. I've been to many kind of space sustainability panel discussions, and in a lot of these, there's quite high-level statements like we should go to green propellants. But quite honestly, if you can't express in numbers what you're talking about, then and when you cannot express that in numbers, your knowledge is of a meager and unsatisfactory kind, as kind of quoted by Lord Kelvin. One solution to this is to look at whether we can actually look at this from a design perspective. So from this slide, what we can see is the fact that most environmental impacts are actually generally set by design choices. About 80% of our environmental impacts actually are set by design choices. And for that reason, actually looking at the environmental impact of space systems and space missions should actually be done as early as possible. And as we can see from this graph, with increased level of definition of the space system, the possible design modification actually decreases in line with the impact of design choices. So for that reason, it's better for us to actually look at the environmental impacts at an early design stage. That is not to say that we shouldn't also be looking at the environmental performance across the other stages of the life cycle. The best place to maybe address this is through concurrent engineering. So this is commonly now being applied to space system studies, particularly early phase studies, feasibility studies. And simply it allows for simultaneous interactions to be made between various experts to design a product in a collaborative and timely manner through the complete sharing of data. And this is very advantageous because it reduces lead times, it produces a higher quality of product, and it also lowers production costs whilst fulfilling customer demands. And really the main elements here is you have a design facility, you have a group of experts who all talk to each other and design collaboratively. They have their own specific software for modeling their own subsystem, and they also have an integrated design tool where they can upload their design to. In this regard, we can integrate what's called life cycle sustainability into this process, and this simply looks at environmental aspects, social aspects, and economic aspects, and integrates this into the technical design. But it's not just one simple stage. We need to have a life cycle perspective. So this means everything from the design and the raw material extraction through to the manufacturing, production, and qualification, the launch, the use, and the end of life. And it's not so simple to say that we have no emissions when we use the space mission because it's in space. Of course, we still have ground stations that we communicate with, which have all got emissions as well. So really this looks to balance products and co-products, energy, wastes, emissions, other releases, human and social capital, and costs and revenue. And the idea is that by running an analysis, looking at all of these areas, we can then come to an impact assessment where we can identify particular hotspots or areas of concern within the life cycle of a space mission, with a view of actually then improving the space system or optimizing it so it has the lowest footprint possible. This is a bit more of a technical overview of what it is we're actually talking about here. So in the concurrent design, you've got different subsystems, each of which feed into this persistent database with their own design information for their subsystem. And the collection of this data is the design of your space mission. This box here is the life cycle sustainability assessment aspect. And the basic idea of what we're trying to develop at Strathclyde is to extract this information and integrate it with our life cycle inventory. So this is essentially a database that has environmental, social, and economic data attached. We can also add our own genetic data to calculate the net footprint of this space mission, to calculate the results, and then we push this through the web service processor back into this database. The advantage of this is that each of these subsystems can then see what the results are and then reiterate the space mission based on these results. The idea, basically, before I move on, is that this process will then continue to repeat itself until we reach a final space mission design. But it's not just about doing this once or twice. We've also got other considerations we need to take into account. So on the left here, we can see that general concept. So you've got our current design facilities, which produce a space mission, and then we can use the life cycle sustainability assessment tool to calculate the impact and put it back into this so it can reiterate. But what we actually found when we started applying this within Strathclyde is that we had numerous results and numerous impact categories. When we were actually redesigning it, we found that while some impact categories may improve, others may actually have got worse, which creates what we call a burden shifting approach. And that then raises the question, what actually is more important, and have you actually created a more robust or more robust design? So one way we can actually solve this is through the use of multi-criteria decision analysis, which looks to apply normalization weighting factors to create what's a single score. So it looks at creating a single score for costing, social, and environmental, which can be added into one sustainability score. This simplifies the decision process and gives engineers who are not familiar with the concept less to understand, if you like, but it does lose a bit of scientific subjectivity. What I mean by this is that, for example, when we have as many impact categories as this, we found that many engineers look purely at one category, which was climate change, because it's what they're familiar with. But actually, climate change in this circumstance may not actually have been the hotspot, if you like, or the most driving factor. This is just an example of some previous studies that we have already used this methodology on. So one is MEOS, which it stands for Moon Ice Observation Satellite, and is also Scottish Gaelic for month, or less commonly moon. It was a spacecraft that was going to go to the moon to, as the name probably tells you, study the ice content on the lunar South Pole. And Neocore was another one that we designed at Strathclyde. It was a few CubeSats that was going to rendezvous with near-Earth asteroids for scientific purposes. And then also StrathCube, which is a student CubeSat we're currently designing at Strathclyde that focuses on space debris detection and also be a re-entry experiment as well. If you're interested in the results of these, there is a paper which we hope to have published quite soon in Advances in Space Research. But beyond this kind of eco-design perspective which I've been taking, we have also done other analyses, such as, like David Humphrey said, we've calculated the life cycle assessment footprint of the Space Energy Initiative's Space Technology Roadmap as well. And in terms of what the kind of estimated global footprint of these space missions were, just in the last slide, we used these two space missions here, so MEOS and Neocore, as a rough impact per kilogram estimation to calculate what the impacts of the space sector were in 2018, according to the activities which took place, but also in a future scenario where the annual launch rate increased to 750. And what we did is we looked at a variety of impact categories you can see here. So air acidification, climate change, economic impact, eutrophication, fresh water and marine, ozone depletion, photochemical oxidation, social impact, freshwater aquatic ecotoxicity and water. And what we did was we mapped these impacts from the annual worldwide impact, so relative to 2010. So this is what we were emitting in 2010, and planetary boundaries, so the ecological threshold that Earth can actually sustain. And in 2018, we found that the space sector's footprint actually was relatively small, so much less than 1% contribution to the impact worldwide and planetary boundary. In that regard, if the space sector was a country, it would have the 73rd largest emitter of greenhouse gases. But when we start to ramp this up a little bit more to the future scenario of 750 launches, we found that actually the impact becomes a little more concerning. So we're getting up towards kind of, kind of maybe 3% worth or 2.5% of planetary boundaries, and over 5% for some impact categories to the worldwide impact. In that regard, we can see that in terms of our CO2 emissions, it would be the 21st largest emitter of greenhouse gases. Now, we focus only on kind of greenhouse gases here, but actually one of the kind of major areas of concern here is ozone depletion, and that mainly comes from the radical compound releases from launch vehicles themselves, particularly solid rocket motors. So just to conclude, what the purpose of this talk is that more has to be done to actually ensure that space itself is sustainable, and everyone needs to play their part. But ultimately, they need to be able to quantify their actions. There is no point in saying, let's go for this green propellant if you can't actually prove it is more green. And a good example of that is that Strathclyde and ESA both ran 2 independent studies where we compared hydrazine to LMP103S, thinking that LMP103S being a high-performance green propellant would absolutely have the better environmental footprint. Actually, it performed worse on 13 out of 16 impact categories. The only one that hydrazine performed better on was actually the toxicity impact categories for obvious reasons. So there's no point in just saying let's do this high level comments like let's just go for green propellant. You need to firstly, before you suggest that as a solution, be able to quantify it as being a solution. And the reason I'm saying that is because the space sector is behind at the moment other sectors, but that is an opportunity because we have an opportunity here to prevent negative trends from becoming the norm going forward. But to do that, we need to get this right now and ensure that the benefits of space can continue to be enjoyed and accessed by future generations. And in that regard, I'm just going to leave off on a quote by Dr. Guy Pignoli, a former astronaut candidate at Kiness. And he says, we're likely to make the wrong decisions if we base our actions solely on cost and political agendas. The most important agenda is the survival of mankind. And what most accords with this should be what we base our decisions on. And the political and financial agenda should be painted around this. It's time we stop seeing the environment as just our planet, but our whole solar system. And I think that's very true. I think I've got just about in time, so thank you for listening, and feel free to email me if you've got any questions or ask at the end of this talk.
Okay. Thanks a lot, Andrew, for the talk, for a great talk, really interesting topic. And please now welcome Krupa Nanda Kumar, please, if you can share your slides.
Oh, sorry, I'm on mute. Yep, just doing that.
So again, for the attendance, don't forget to put your questions in the Q&A box, and we go over that just after this presentation. Yes, we can see your slide.
Yeah, super. Okay, fantastic. Thank you, the Catapult, for having Space for Climate today. Most of my panelists, well, I think all my fellow panelists have spoken or taken all of us out of space. I'm going to bring us back down to earth, in a sense, and speak more about some of the services and applications closer to home that are being developed, that are currently in process of being, going from an emerging technology to something that's quite feasible, and also some of the new innovative sensor technologies that will be going up in space that can help us aid climate actions towards net zero. I wanted, for those of you who don't know about Space for Climate, I'm going to give a bit of an introduction, and you'll understand why I'm going to be talking about a lot of things that I am going to be today. So Space for Climate is to emphasize a non-for-profit organization chaired by the UK Space Agency. The primary mission here is to ensure a seamless supply chain of trusted climate data from space, so that UK offers a growing supportive environment to the development of EO products to various sectors, both locally and globally. Member organizations within Space for Climate span SMEs to multinationals, government policy agencies, third sectors, and other funding bodies as well. The group represents UK expertise involved in climate Earth observation data, right from the mission creation, data set collection, so the data acquisition, verification, quality assurance, so going towards the downstream, through to the analytics and the packaging of that ARD information to applications that can be used by the end users who not necessarily will be fluent in the kind of services that we provide. So we often try to combine a lot of the work that we do with data sets to produce a value add to support the decision making. At this point, we spoke a lot about outer space, solar-based power, and launching satellites to do that, or rather apparatuses to do that. I'd like to touch upon some of the current critical UK investments in some crucial climate missions that are going to really either disrupt, we don't know yet, but definitely revolutionize some of the way we collect climate data and the kind of climate data sets that we will be able to collect in the future as well. To start off with, Truths is probably the main important mission to talk about here. It was conceptualized by NPL. It's being led by the European Space Agency, but designed by the UK. It's essentially going to be a lab, a scientific lab in the sky. It's going to set the gold standard for referencing climate measurements which can also help further reference existing satellite missions that are orbiting as well to improve their accuracy of existing missions and new missions for the data that they collect. This is going to be launched further later on in the decade towards 2029. However, your microcarbon, your biomass is something that's more that we can realize quite soon enough. So microcarb, again, it's being led by ESA, but it's we've got several UK partners involved like GMW, NPL, RAL Space, University of Leicester, Edinburgh. It's the only and the first dedicated European mission to measure carbon dioxide, and which is obviously one of the primary greenhouse GHG gases. It will have special tasking facilities to sort of city scan over tasked areas to map CO2 emissions across industries or cities that are notorious for those emissions, and quite rapidly have that information downstream as well. The mission itself has come about to help countries and help nations monitor their IPCC progress against the Paris Agreement climate targets. So essentially the NDCs that have been set against the agreement. And lastly, the biomass is something quite close to the UK because it was invented, conceptualized by a scientist up in Sheffield. Airbus is the prime contractor, and this is the first satellite, I believe, that will use sort of the P-band spectrum as a sensor on satellites. It is, as the name goes, it's dedicated to calculating, tracking, and understanding biomass emissions, which is obviously, as we all know, biomass especially in wetlands, in green inventories like forests contain a lot of capture and contain a lot of carbon. So it's a huge critical metric or a measurement for us to understand all the trapped biomass in the green inventory. So these two missions, the ones that are coming up quite soon enough across the horizon, going to really propel that understanding of climate actions towards net zero. But just moving on to sort of, the second half of my presentation to close down on some of the existing but yet evolving tools and applications out there to understand net zero actions better for industries across the private and the public sector. I'm sorry, I keep shifting, but we've got a consortia within Space for Climate made up of Fort Worth Intelligence, the King's College, Digital Globe. I'm sorry, I apologize. I'm just going to see why it's not on slideshow mode, but it just keeps changing. Anyway, sorry, apologies for that. The Earth observation for air quality modeling and traffic emissions has been a very successful project by members within Space for Climate. It's been used by local authorities to identify sources of emissions, particularly around vehicles, so transportation, channels, as well as building emissions and other like sewage structures and whatnot. So the it's led by Fort Worth Intelligence. It's a quality air quality product that can model hyperlocal pollution levels at a citywide scale and at a nationwide scale. So the spatiotemporal coverage is quite broad. And it's a reliable metric to understand the CO2 emissions, especially for local authorities against moving vehicles. I will now move on to CRISP because my slide's just moving to this. So CRISP is a very powerful tool, and this is something that we're really pushing within Space for Climate, is because we understand, I don't know what's going on with my slides today, I apologize. I'm just gonna see if I can, just going to stop sharing for a bit and try to get out and see what's
Krupa, do you think you can maybe conclude now? I don't know if you need your slide to conclude, so we can move to the panel discussion if it's okay for you.
Yeah, absolutely. I'm just going to quickly, I shouldn't take more than 2 minutes. on this, if that's okay.
Yeah, we are running a bit behind, but yeah, if you could make it like a
Absolutely.
from conclusion, that would be really appreciated.
Absolutely. Yeah. I'll just, I apologize for the I haven't set any timer on this. I don't know what's going on, but just really quickly on the CRISP tool, I just wanted to stress that I think we all understand that those who control the finances control a lot of the decisions. So it's really important for us to enter the spatial finance sector, and that's what the CRISP tool does. It brings together quality assured Earth observation data using historical reanalysis of the satellite information to understand sort of the spatial against nationwide and local requirements against some of the metrics that I've mentioned here, which I won't go through. Finally, I've just wanted to also touch upon energy metric, which is a really useful tool from the IEA to understand the due diligence that industries need to do towards net zero. I won't go further, but just to conclude, just a snapshot of some of the satellite services that are supporting the current global stocktake activity, which is being carried out across the nations. We did this exercise towards the Living Planet Symposium, collecting all the good work that's being done within the UK towards understanding and capturing all that stocktake information. This is an activity that's going to be run by the UN from 2021 to 2023. So we'll see more of this towards mitigation and adaptation for climate and net zero. And lastly, to conclude, I just wanted to say that Space for Climate, we ourselves are going to be entering the party on net zero. We are formulating and working on a net zero activity ourselves for our members and the wider community to identify priority areas that are most need for decarbonization across industries. So watch out, follow us on our socials and watch out for the Space for More. It'll be something very exciting to get involved on behalf of the entire UK ecosystem. And lastly, I wanted to just stress that there's for those of you who are interested in this domain, a very important conference is the UK EO conference, which is the largest Earth observation conference. Please, I haven't put a link in, but please just type this in, and it's really important to be part of, should you be interested to learn more about some of the activities that the UK sector is doing in this space. And thank you. Apologies again for the erratic slides.
Thanks a lot, Krupa. That was a very interesting talk. So now if I can just ask all the panelists to reactivate your webcam so I can see you. I have a wee question to start off the panel discussion. So I wanted to have your opinion. So the assessment clearly shows where we are and where is our targets. And we have seen through your presentations, great solutions. But did you identify any potential risks, red tapes, or lack of funding in the development for the full potential of those ideas? Or do you think it's just, in the good way and just a matter of time until you're able to solve those problems? So does anyone want to give their opinion on that?
Yes, I'm happy to start. So in terms of well, if we're going to launch one of the largest structures our species has ever developed, there will be many risks. There's actually a question in the Q&A, actually, basically talking about parking slots. There's many technical risks that we need to resolve. Wireless power transmission, robotic assembly has been done, but it needs to be industrialized. And of course, there's a manufacturing and logistical issue that will be in my opinion, one of the biggest challenges for space-based solar power. But of course, there's this regulatory aspect. We're going to be looking at using between 2.4 and 5 gigahertz. That's going to have to be regulated in some format. We have a regulatory working group for the Space Energy Initiative that is looking at that. And of course, we need parking orbits for GEO to park a kilometer-sized spacecraft. And I would imagine I might annoy some of the comms satellites people, sorry, Paul, when I try and park a rather large spacecraft. These are all activities that we know there's risk involved in that. However, again, we think the technology is so important and we are such a race to net zero that these technical and regulatory risks are worth trying to solve and trying to solve fast.
Thanks a lot, David, for that. Really good points. Anybody else want to touch on that, or we can maybe move to the question by Paul? No?
I have a couple of things to say. I think same as David's. I think that the tall space concept is also relying on a large structure. I think in terms of some of the technologies for reflectors and so on, it's available through solar sailing, but still making it a big structure and controlling its space involves some risks. Financially, I think it's also a big undertaking, and right now there's no financial source, and it's an academic study at this point. But I think there are good potentials, particularly because using multiple solar power farms, it kind of invites multinational efforts or multi sort of corporal, I guess, efforts. So I think there's a bit of opportunity, and at the same time, similar risks involved. But I think it's an applicable technology in relatively near term, just because it's already flown by means of solar sailing. So I believe it's both risks or opportunities are there for this concept as well.
Thanks a lot, Ono. I just wanted to bounce back to a small question regarding this ground concept that many of us really see as, the solution for the future. So we've seen in the past years that peer review scientific data is not always enough to convince, public acceptance in some cases. So I wanted to know, we are aware of some potential issues with space-based solar power or solar reflectors. I wanted to know what was your take on what are the actions you think are needed in addition of the technological demonstrations to increase, public acceptance, and thus, if we have more public acceptance, we're going to have more funding for those issues. Did you identify anything in this regard?
Yeah, so I've actually come from a very nuclear background, so I did fusion research for many years, and I've also looked at fission, for instance, looking at the SMR program and developing that for space. Social acceptance is obviously absolutely vital, the way that we engage with the public, the way we bring them on that journey, but it is in some regards a bit like how we talk about the current levelized cost of electricity, and can we do future energy production to meet current levelized cost of electricity. In some respects, that is a little bit of a false journey to go on. As we start going into the next decade, as Amanda's has already said, we are going to have increasing fire, increasing flooding. We are going to get to a point where we will need to make decisions, whether it's not in my backyard, a wind turbine or a rectenna or solar panels or a nuclear power plant, or do we want that backyard on fire? And so, yes, we need to take that journey with the public, but also we need to show them that these technologies are valuable commercially. We believe that the spin-outs and spillovers from space-based solar power can mean that there are many different, whether it is help with space assembly and robotics, whether it is wireless power transmission in the home, we can show that there's a valuable journey. There is growth to be had there. There are jobs, there are PhDs and masters to be there. So it's not only showing them why we need to do that, but where that value is along that journey. So yes, but public perception will change as we start to see the looming climate crisis actually happen to normal everyday people every day.
Thanks a lot, David, for this good overview response, and I'm glad none of you are using your technology for a death ray or anything like that. Paul, you touched on a really interesting question at the beginning of this webinar, if you want to come back onto that.
Yeah, thank you, Gilles. And we only have about 10 minutes left on the call, is that right? 15 maybe?
Just below 15 minutes.
Okay, so maybe I could pose a few questions that the the panels could consider for the next couple of minutes, and then what we'll do is a wrap afterwards. First of all, I'd like to thank the panelists for such a wide-ranging set of concepts that they put in place and challenges that we face. I've got some, because this is a technology-focused presentation, it's about the future forum. I'd like to ask each of the individual presenters to consider one thing. What is the major technological priorities that they would see necessary in order to actually address the challenges? And I'm going to ask a couple of focus. First of all, with David, with regard to tackling potentially energy poverty, resilience of infrastructure and things, if you could touch on in a moment the aspects of the deployment of infrastructure and the cost models for this, and where you see the significant technologies are. Oh no, one of the challenges I think we might face with the large structures that we're describing here is perhaps aspects of focusing of the structure, or keeping the attitude control in the orbits. If you could say something about the challenges there. Andrew, the sort of things that you've been describing in terms of measuring the impact of the space economy on the global economy, could you touch on whether things like the large-scale reusable launchers are a significant contribution towards addressing these challenges moving forward, because it's a different scale and maybe it's on a roadmap. Krupa, you've touched quite a lot on these missions that are really helping us to measure the impact of human activity on climate change. Can you consider perhaps what do we need to do to actually move the international agenda from observing the status to actually investing in infrastructure and capability that's going to change, and your perspective on the international stage? And then perhaps Amanda, if you could then wrap for us on that perspective of how do we mobilize the global communities at regulatory levels, at international levels and industrial levels, and what are your perspectives? So I've told you all the questions I'd like to go through. You've got 2 minutes on each of them, and then we'll wrap at the end. So who'd like to go first?
I'm happy to start if you'd like. So main technical challenges in terms of space-based solar power is the wireless power transmission over long distance at high power densities. When I mean high power densities, I'm actually only talking about 250 watts per meter squared. So that's kind of half the midday sun. And the other challenge in terms of technical is the ability to ramp up the logistics and manufacturing. As I said before, this needs to be considered very much more like producing iPhones or Samsung phones, not getting into an iPhone versus Android debate. And so those logistical challenges of creating a gigafactory where we don't know what the production line is. You also mentioned making sure that we are an equitable power source. One of the beautiful things about the particular design we're looking at is we can have different size spacecraft in different orbits. So if we look at our phase 3, we will be delivering a spacecraft which can deliver power in the tropical area. So not only can we deliver to, for instance, some of our paying customers, whether it's Australia, whether it is in the Americas, but also we are also going over some of the developing nations. So you can see where we could put infrastructure up, which allows us to also deliver for less cost to those developing nations where they can jump across that fossil fuel need. One of the beautiful things, just to finish off on space-based solar power, is the power supply itself is an interconnect. So it's not like making a solar panel in the middle of the desert and then having to have interconnects to the point of use. We can point anywhere. And so we can make sure that when a country is got lots of solar, a lot of wind, let's point the beam somewhere else that actually needs it. So we want it to be an equitable power system so much we put it within our vision.
Thanks, David. Oh no, I don't think this is a competing for technology. We want to race to do everything. So tell us all the challenges to get the reflectors in space.
I think, I think one of the things that I really like about orbiting solar reflectors is that it's quite flexible and it's quite decoupled from the terrestrial system. So, and the way we the type of energy is quite intuitive as well. It just delivers the sunlight. So wherever the sunlight is needed, you can actually turn your reflector there and help really for the whole of this sustainability problem. But I think which means also to be able to control and avoid unwanted sunlight going in different directions on Earth. And it's not exactly my area of expertise, but we are working on the control strategies to avoid such disturbances and developing different strategies to avoid for it. After we finish servicing a target, we just like turn the reflector away, or deriving a control strategy that just avoids the sunlight going into different directions on Earth. But it's again having a structure, potentially larger than ISS still means that you need a big control system. So one of the solutions is so instead of one big structure, having multiple small structures that constitute the same amount of area, or there's also a limit on that, how small you can get, because then otherwise you run into the problem of manufacturing so many things all at once, or at the same time. And there's some balance in between, and it's possible to just make things smaller and more controllable at the same time, develop strategies to make them happen. But just on top of David's point, and this control strategy means like being able to control these things means you can basically again service this, and this was one of the ideas that I was thinking as well. You can actually encourage sort of international collaboration and new solar power plant locations, potentially in developing nations, and the areas of high solar installation, but no infrastructure for solar power, can actually enable that. And with the technologies, it's just like it kind of connects together, and eventually.
Move on. That's great. I see there's some real challenges. Andrew, obviously from a whole system sustainability, it's not just the launch, but has a certain impact. Do you want to say a few words?
Yeah, so I think the default when it comes to thinking about emissions in the space sector is always the launch event. It's always the default, but it's not generally the launch event that can cause the biggest impact. But I'll put a pin in that, come back to that just in a second. Large-scale reusable launchers, can they actually reduce emissions like you asked? It's a bit hard to answer because it depends on many different factors. Yes, you're going to be reducing resource dependency, which in itself is a good thing, and you're going to reduce expendable stages going to the ocean, which then has an effect on aquatic life. But by creating reusable launchers, you immediately need more propellant, which again has an impact from the production and manufacturing of the propellant and the actual emitting of exhaust products into the atmosphere. You also have emissions from the recovery of from the launch site and bring it back to be refurbished in some way to be used. So it's not quite as simple as saying that. However, I have released a conference paper, so a shameless plug here, called Eco Design of Future Reusable Launchers, which is freely available for you to read. It's from UCAS, so we released that last month, which is on that on this topic. But as well as that, there's different parts of the launch kind of segment, if you like, that you need to also consider. Where is the launch site? What's going on in the launch campaign? Is the production of the launcher itself, and the likes. And a big thing that's really been holding this back, I'd say one of the main challenges is that a lot of the life cycle data sets on launchers are highly confidential. In fact, in the European Space Agency, there's only one named person who's allowed to see the data sets on launchers, because these companies don't want to be seen as the outcasts, or as they put it themselves, the black sheep of the industry, which again is problematic, because how can you then quantify your impact if these data sets are then being withheld? So there's a need to be more upfront, more transparent, and in that regard, we are starting to see movement in that. So the European Commission has recently drafted a terms of reference for a product environmental footprint of space systems. The ESA have poured more than 20 million into studies. And also in Scotland, where we've actually got an environmental task force which is looking to actually create a net zero space sector in Scotland. So there is movement on it, but like I said in my presentation, the first thing we need to do is be able to quantify this and say how much better is a reusable vehicle versus an expendable vehicle.
Super. Thanks, Andrew. You've actually covered both of the things that were buzzing around in my head, which is the difference in scale of, and also some of the aspects of reusability. And we only just have to think about our cost of things that we do around the planet, whether it's fly in an aeroplane or get in a car and drive. I mean, it's not only the cost of fuel, it's the cost of manufacturing the vehicle as well. And those things are, obviously a big trade space. Maybe we'll come back to that. So, Krupa, your thoughts really, and please feel free to bring us back to earth as well.
No worries. Paul, well, you've actually asked me quite a political question, but I'm going to steer away from that and just say that I think there's a lot of evidence that there's increased manufacturing coming out of the UK towards launch capabilities. It could either be like small sats or sensors or just an entire rocket itself. So there is a lot of push towards that infrastructure being set up on a national scale. But I think we do have to understand that a lot of the missions need to focus on the gaps, on sort of existing gaps that will help policy towards 2050 ambitions. There are a lot of activities being run to understand technological gaps for GHG emissions, for example, methane monitoring, and that will then allow governments to inform on the launches that are required, will obviously trickle down to the infrastructure. So yes, I think we will see a lot of that in the coming years in the country.
Okay, well, we're going to come back to this as we'd have a bit longer. I discovered I was thinking we'd finish at 11:30, but we don't. So I'll let the conversation go on, but we'll come back to this wider question. Amanda, your thoughts really on what you've heard today, how it might be able to contribute. In fact, really, what do we need to do? Coming back to this aspect of organisations operating at international scale, the role of government and the role of industry.
Definitely. Yeah, really enjoyed today presentations in so many different perspectives, barriers, challenges, and opportunities. Linking it back to net zero and really the problem statement. Essentially, if one sector, one organisation fails, we all fail in net zero. We live in an ever-connected world, and the cost of the consequences of climate change far outweigh the investment required to achieve net zero and the innovation to drive that. So I don't see any of the technologies today or others essentially competing against each other. We're all aiming for the same goal and the same solution, so we need to support each other on that. But it's really important that we're not repeating the same work in the same areas, which is often the case in lots of sectors in innovation. It's important that we're running out of time on this, so we need to make the most of our time, our resources, and play to our strengths. Particularly for the UK, position itself as with its academia excellence and UK science superpower. So really getting the expertise and the understanding from the academic community. There's also an element of humility here of actually what are our barriers as well, what are our weaknesses, and working with the international community to really bring those up and support us on them. So we need to take other countries, other organisations on the journey with us with the innovation. We're on the same goal, and it's really an unknown here in lots of the areas, but we need to strive towards it. So to summarise, in order to mobilise the global community, it's really about collaboration, playing to your strengths, working with organisations from academia, industry bodies like Space for Climate, really to drive and guide the UK on policy, the innovation that we need, policy to drive the innovation. And webinars like this as well, sharing best practice, talking, discussing, and asking for support in areas you need.
Thanks, Amanda. I'm going to spend just a couple of minutes just reflecting on the question. I know that people have been trying to answer the questions, but I'm going to acknowledge the questions from the audience and the people. So Mark Loveday had posed a question with regard to the congestion in orbits, and I think this is not only for geostationary orbits, but it's also the congestion in in space in general, and whether we see some of these future systems that are being deployed as actually having to juggle around and get some elbow room to actually be able to actually operate, and some of the challenges. So I know that David had some attempt at answering that, and anything you'd like to add about that? Anyone else like to add with regard to the consideration with regard to access to space in terms of orbital configuration and coordination for operations? What kind of challenges do we think we'd face, and how would we overcome them?
I'm just going to touch on something which Andrew mentioned earlier about the complexities of different sustainability issues. When I think about space and congestion, I like to think it's essentially another ecosystem. And if you think of how with microplastics and pollutions in the oceans, essentially we have another ecosystem in space, and we have potential to cause significant damage for future generations. We really need to learn of the mistakes that we've made here down on Earth, take a very systems thinking approach. Sustainability is a very, it's called one of the most wicked problems. And by that, I mean, you may be doing something positive for climate, but it might have a negative impact on biodiversity, pollution, etc. So taking this whole systems approach, thinking about the consequences and weighing up the decisions. And again, linking back to the humility, ask people with different perspectives what they think and know the consequences in the future. Being able to pivot decisions.
Andrew, you want to respond to that?
No, I completely agree. It's unintended consequences. So, for example, we're hearing a lot of, for example, mega constellations which are being proposed to put up into space, which is just going to add to orbital congestion and, potentially even cause collisions with space debris, which causes the Kessler effect, more collisions, so on and so forth. Beyond the impact of orbital congestion, then the problem is how, at the end of our life, do we get rid of these things? And the default has been deorbit them to burn up so that they're not adding to this orbital congestion. But that, like I said in my talk, in itself is then creating a rain of metallic compounds and putting that into our atmosphere, which again could be complex. So, it's weighing up, is that actually a good solution, or is that going to have negative consequences? Space, I completely agree with what Amanda said. I see space itself as also an ecosystem, and there's also work that's been done in actually suggesting that space should be an SDG in itself, should be the 18th SDG. Again, if you look at what the most sustainable option actually would be, it would be for humans just to leave space alone and let it self-regulate itself. The stuff in space would eventually come down, albeit thousands of years, but that's not socially or politically acceptable to do. So if we're wanting to continue using space, we're going to have to take that systems approach, like Amanda said, and actually think what is the best solution, and what, is it going to be deorbiting? What will the net impacts of that be? Or can we actually recycle in space, for example? There's a project going at Strathclyde looking at how do we recycle large platforms like space-based solar power in space, albeit it's just kicked off. The first kind of paper will be produced will be presented at the IAC this year. But it's rethinking how we actually do our operations and knowing that we can't continue in where we are, or space is going to be inaccessible, and we're going to lose the critical services that we rely on in our lives today.
Thanks, Andrew. I think that's really a good perspective to bring. I think we should, as you rightly point out, acknowledge that the infrastructure that we put in space brings benefits, significant benefits, and it actually has a positive contribution on the pathway to net zero, even today, with the infrastructure that's up there. But we've got to be able to make sure that we sustain that into the future. David, you described some things earlier where you were saying that the spin-offs that come about from trying to put this infrastructure in space and operate it. Do you think there are things that we can do to make space more sustainable while we're actually putting the infrastructure up there?
Yes, so I think, again, just to go back onto the points that both Amanda and Andrew made, so we should do a full sustainability assessment of what we need in infrastructure in space to support our planet. I believe that space-based solar power will be naturally included in that assessment, because I believe that we have so little baseload energy sources apart from fission that space-based solar power will have to be included because it just gives you a new baseload technology. When you looked at, when I showed the slide which showed the criterion that the Space Energy Initiative is working for in terms of space-based solar power program, we use the word sustainable in there. We believe it's more sustainable because when you look at the minerals, and if you look at some reports, it looks like we need to have a 6-fold increase in mineral resource usage as we start to move towards 2050. We believe when you look at space-based solar power, the technology uses significantly less. So when we're designing this this system, we can't make the mistakes that we used to make. We can't make them. So we have a nuclear legacy primarily because we rushed to fission. We have a space legacy of debris because we had a race to try and get things into space. And so our design will be as much about sustainability as it is for manufacturability and assembly in space. We think that these go hand in hand and you can make money out of it. So it's not just some noble goal. We believe we can make return for our investor, and we think we can be equitable and sociable and actually have scalability and actually have this sustainability throughout our design. It's going to be difficult.
I understand, and I think this is really helpful. I'm just going to acknowledge Ben Merton's question, which you also tried to respond to in the chat, which relates to the efficiency and the cost of today's solar power capability in space, the total powers that we put on spacecraft to survive the environment and to actually exist for the entire lifetime of the satellite. They tend to be quite expensive and heavy and all the rest of it. So what Ben is highlighting is that the fact that we're probably a long way away from hitting the efficiency levels that you suggested we're going to need to make space solar really effective. Do you want to just touch on that before we move on to the other data related questions?
Yeah, so the particular design that we are focused on is quite different from other space-based solar power design, where we are both sun pointing and earth pointing. So where you look at other space-based solar power designs, for instance, in China and Japan and in America, portions of their satellite are not in the sun in certain parts of the orbit. And so we have a quite clever design which allows us to use all of it. Also, when you look at we actually have a really short path length between what receives the sunlight from the reflector and the actual RF transmitter. So we're actually trying to reduce both mass, but also in specific decrease specific mass by having these really sparse structures where the high concentration PV is on a very almost foldable electronics into the thinnest, most sparse antennas. And so we believe that we'll never hit the 1 kilowatt per kilogram in our initial, but we think we can, through efficiencies in manufacturing processes, start to move towards there. And when you get bigger devices, of course, there's an economy of scale. So my first 6 megawatt device is going to be very heavy for what it delivers. But as we start moving to this sweet spot of around 1.5 to 2 gigawatts, which is similar really to a nuclear new build, they're rather kind of 3 gigawatts or so. That's a real sweet spot of where we move to that 1 kilowatt per kilogram.
Thanks, David. So I'm going to switch to a couple of other questions that will look beyond the technology as well. We've got one which Andrew Forney from Astrosat asked, relating to the need to create awareness in the wider community with regard to the opportunities. And he's mentioned specifically financial sectors and insurance, which Krupa's had an attempt at responding to. So maybe I could open that out to the panel in terms of the aspect of investability of these kind of infrastructures, creating awareness, and also for the adoption of the output. So Krupa, do you want to start by vocalizing your answer to Andrew, and then we can just open it out to the rest of the panel?
Yeah, thank you, Paul. So just to iterate what I've said, I think there's been huge emphasis, especially since the TCFD, which is the Task Force on Climate Disclosures. It's all starting to become regulations within governments towards the private industry. It's starting to become mandates. So there's a need for the traditional bankers and fund managers to start speaking the language of ESG, sustainable finance, incorporating spatial finance tools in their back-end dashboards to verify the transparency of the data being disclosed by companies, especially the notorious ones across the oil and gas and the mining divisions. So we at Space for Climate, we've got a task groups specifically focusing on those tools that can be incorporated either by intermediaries like the ranking agencies or by the financial institutes themselves. There's a big push by UKRI through the CGFI, which is the Center for Greening Finance Initiative, from the Oxford School. They're leading a fantastic initiative on sustainable finance. So I would urge you to look into that and also talk to us. But it's a very fragmented sector at this point, where everyone's grappling to understand how they can incorporate spatial finance tools. But just to complement some of the things that my panelists have said is also for the financial institutes to look into investments into space-based solar power as something that they can show against green bonds and green investments that they're doing, the same way that they would do for nuclear or hydrogen power. Really, so that narrative also needs to be focused from hydrogen, nuclear, and solar-based as well for investors and financial institutes.
Thanks, Krupa. Before we move to the other questions that are in the Q&A that we haven't answered yet, Amanda, you have your hand up.
Yes, just to add to that. So there's been a transition from sustainability, essentially like showcasing exciting innovation, almost kind of greenwashing, and towards the transition to ESG, which is fundamentally about data to inform decision-making. That's specifically actually why I joined the satellite application catalog, because there's a gap in identifying and quantifying the solutions and informing the decisions to drive net zero. So to support the finance sector, which would have a knock-on effect on all the other sectors, you need to essentially monitor, quantify the impacts, and that should be the leverage to then sell the innovations and compare them.
Thanks, Amanda. That's interesting. So we do have one question that hasn't been touched on yet, and Sally Stevens has raised this in the chat. And her question is, and it's responding to the current discussion and the key challenges to make sure that the data that comes back from these missions is available for the analytics. And she's making the point that the UK Climate Services community is ready to hit the ground, but we need a UK investment to turn these missions into climate action services. So maybe Krupa or Amanda, you want to comment on this question that's raised by Sally? Gilles, if you have a few points.
No, absolutely. I think Sally makes a fantastic point. There is, you need to have justification against these missions to extract value out of that, and it's very hard to understand during the conceptualization of a mission as to how the downstream usage is going to look like. And I think all of that needs to be made clear as part of the life cycle towards launch, to encourage the community, to even inspire funding streams and funding channels to get the discussions going, and to also allow the private industry to plan, to budget, to plan for innovation internally, because these launches are going to go into commercial service soon enough. So I think we still don't have those disciplines in place for the industries. And I think that's something that the government and organizations like Space for Climate can support on, and private industries come together to see how we can pre-plan to really exploit the missions going ahead.
Thanks, Cooper. Anybody else want to add to the insights that Cooper has brought?
Yes, I'd like to add the external perspective from other sectors isn't as often as positive as how we like to talk about the applications. And essentially, there is a lot of the reputation of our sector and the opportunities from them aren't fully known from both the finance and the knock-on effect of the other companies. And so it's actually really critical that we are working, collaborating at the very early stages to identify and showcase what these opportunities are, embed them so they're kind of grabbing up these opportunities and supporting them as we develop these missions.
Thanks, Amanda. Gilles, as co-host for this session, we've covered quite a lot of ground. You might have been seeing a few points, other discussion points that are in the background as well. Is there anything you'd like to bring to the panel or your own insights?
Yes, so just before I do that, we have about 5 minutes. So if anybody in the audience wants to ask a quick question, please put that in the chat. And while you're doing that, and I bring the point of Paul, Eddie, do you want maybe to make the quick announcement regarding the location of this recording?
Sure. Yeah. Thanks, Gilles. So yeah, I'm really pleased that this has been a really insightful webinar. Great talks from all the speakers and great questions from all the panelists. So this has been a recorded webinar, and as with the previous emerging technology webinars in the series, we will follow up with a blog post, and the recording will get posted on the Satellite Applications website. So do look for that in the next month or so. So I'll hand back over to you, Gilles. Thanks.
Okay, thanks a lot, Eddie, for all your work in organization and on all of that. So just on the background, there is a lot of questions again regarding feasible, technical feasibility, things like that, and there is some really interesting points which have been touched lightly. And unfortunately, we do not have like a full day to talk about that. David mentioned quickly that the energy was transparent to the atmosphere, and the worst case of bad weather, it was about 6% loss. But I wanted to have maybe the point of view of Onur on his own solar reflector technology, or the technology of his group, and how does the reflected solar light affect the irradiance balance of additional light, and is this an issue, and is it governed?
Right. So I think we have a very sort of low order approach to this. To be honest, it's not as complex as some of the other approaches in terms of energy balance. But I think the point is obviously the sunlight that is put to the atmosphere is actually lost in some way. In a clear sky, it's lost in some percentage, because atmosphere has a transmission efficiency for this kind of like sunlight. But and the remaining is somehow lost as a heat. But when you remove, say, a conventional coal-based power plant, or the amount of coal, let's say, to be spent, or a fossil fuel to be spent to generate that much of energy from the system, in the overall, we are sort of in the positive side of things. We add some, but we actually take out more from the system. So and when it comes in terms of I think it was like a more weather related question as well. So obviously one of the main challenges with orbiting solar reflectors is well, when it's cloudy, it's actually quite hard to get sunlight to the ground. And the way we approach to this is mostly part of my research deals with this is using reflectors as solar sails and changing orbital planes and make them flexible for seasonal variation. So if there's, say, one part of the Earth is cloudy and we cannot service those solar power farms, then maybe we can allow, I don't know, 5-10 days and change the orbital plane and go to some other location and service that. This is sort of our approach to overcome that limitation. Although I guess I must say that the research on the transmission through cloud is quite scarce, or it's just limited to only certain local areas. There's like more studies on how the actual transmission efficiency changes needs to be further studied, I think.
Okay, so if I understood clearly, this is a call for additional funding for technical demonstrations. That would be welcome. Before I hand it out to Paul for the closing remarks, I have a small question for Andrew. So if you can maybe respond quickly to that. So the concurrent design approach with, including the life cycle analysis, something which, I believe has a very strong impact, and I hope that other people will be as eager as I am to read your article. But I wanted to know, because we don't see this approach, being widespread in the industry. So do you see, any specific barrier to entry for all actors to actually adopt this methodology, or is it just a question of time and a question of educating a new generation of engineers?
Okay, so firstly, I'll explain there's eco-design and life cycle assessment are two different types of assessment. Eco-design is life cycle assessment applied to design activities that are ongoing, if you like, so actually happening. Life cycle assessment can take place at the end of design sessions. So just because you don't do concurrent engineering or concurrent design doesn't mean that you cannot use life cycle assessment. So that's the first thing. Life cycle assessment in the space sector, well, life cycle assessment as a whole isn't new. It dates back to the 80s, the 70s, 80s, but in the space sector, it's only kind of the last 10 years that it started to take off. And when I started my PhD in that topic in 2016. By about halfway through it, I thought, am I specializing in something that the industry just doesn't care about? But luckily, we're starting to see a lot more interest from companies now actually taking a direct interest in this. We're seeing SMEs starting to form space sustainability. We're seeing, for example, with Dave, we've been working with him to actually create a life cycle assessment for the UK Space Energy Initiative and their technology roadmap. Space-based solar power, of course, being a sustainable option, you've got to do what it says in the tin. And by doing that, hopefully we can attract more funding to keep these studies going and do eco-design throughout that design process to make sure that we're actually creating a system that is actually as sustainable as it can possibly be, as it technically can be. And that in itself may actually create more jobs. At least I hope it will create more jobs as well. But we're also starting to see a lot more interest in this. So we've seen this space sustainability rating system. There's a possibility of life cycle assessment maybe included in a module in it as well, which would add more emphasis on it. But we're seeing more and more people working in the area. There's many PhDs now who are starting to look into eco-design. And it's not just about merely compliance purposes or corporate social responsibility, and it shouldn't just be seen as a tick box exercise to say we've got our carbon footprint. It needs to be done in a way that can contribute to actually lowering the environmental footprint as far as technically possible. And that is really the crux of the problem. But there's more interest, there's certainly more jobs, and really it can be seen by companies as being a cost-saving exercise where you can actually not just save some CO2, but also save on your underlying costs as well.
And with that in mind, I'm afraid I'm going to have to call it now. And I see other people got a hand up. So Andrew, thank you. You could all, that is a great summing up anyway. I think this is really passionate a presentation of the fact that we've got to get our own house in order. And we've got to do that, because if we don't, then we won't be respected. But I think what we've seen today is that there is some really significant opportunities for the space sector to contribute towards the pathway to net zero carbon. We've got to work the international community. We've got to work the whole of the wider ecosystem and bring an understanding of the benefits. We've got to make sure that we do things ourselves sustainably, but we also look at it from a systems perspective. And the aspect of doing things in space can be a lower impact way of delivering what we need as a society on a global scale moving forward is really important. So a fantastic presentation. Before we close, I'd just like to pass the floor then back to Eddie, just for one last point to talk a little bit about, just mention future sessions. But right now, I'd like to thank all the panelists and my co-host Gilles for really making this a very powerful session today. And I hope everyone in the audience and the people that participated in questions have managed to get something out of it. I certainly did. So Eddie, do you want to just say a little bit about our next opportunity for getting together?
Yep, brilliant. Thanks a lot, Paul. And I'll just echo those words. Thanks again to the panelists. Thanks again to the audience for your questions, and for Paul and Gilles for your co-hosting of the webinar. It's been great. So this is as a series, as we said at the top of the call. And so this is the 5th webinar in the Emerging Technology series, which is co-hosted by the Catapult and the University of Glasgow. The timescales for the next webinar will be in the early winter time, so probably around October, November. We haven't fixed a date yet, and we haven't fixed a theme yet. So really, if you do have any ideas for the theme of the next webinar, please do share some ideas with us. We'll be really open to ideas. We are thinking about the changes from when we started this series just under 2 years ago to now, that we now have a number of strategies in place, so we could reflect on the changes of the space sector from when we started this series to where we are now. But as I say, more than welcome to hearing ideas, and the next webinar should be in a few months' time, around October, November time. So I'll pass over to you, Paul, to say the final thank yous and farewells.
The final thank you goes to you, Eddie, for really bringing this series to life. Well, thank you, everyone. Stay safe and stay green, and see you at the next session.
Thank you.
Thank you very much. Stay green. Yes.
Bye, everyone.
Bye.
Hi, Rob. Is that you still there on the other side of the line?
Yeah, hi Eddie, how's it going?
Yeah, good, thank you. I just wanted to stick around about the the pausing and stopping of the recording.
Okay, cool. And that was really interesting. Some really, really interesting, insightful stuff there.
Yeah, thank you. Yeah, these are usually really quite insightful webinars, bring a wide variety of thoughts together.
When's the next one? So the next one's winter time, you said?
Will be, yeah. We haven't fixed the date yet, but yeah, we do this twice a year usually. But we kind of got a little bit excited. Oops, Paul's just calling me. I just couldn't send him a message. Yeah. So we usually do this twice a year, so sort of April time, October time. But we got excited with ourselves with this space-enabled net zero by 2050, and thought that we could probably eke more out of it than just one. So we've done this one as a two-parter. So yeah, we did one in May, and then obviously this one today.
It was good. There's really active discussion on everything. I think everyone was eager to have that panel discussion, I think, was really back before. There wasn't just one person looking for an answer. It was really good.
Yeah, that's right.
What in terms of the recording? So that is that's both co-hosts and yourself and I have the recording stored, or?
Yeah, so I think that what happened with the previous recordings is that I didn't manage to get access to it, even though I'm a co-host. So I think that
probably pause
you
it
guys
out.